Okay, welcome back. Good morning. Wait me for a second. Let me just get my pen. Okay. Well, what I want to do is to look at reactance and impedance. Okay, and just sure I can get it up. So I can get it into focus. That's my main concern at the moment. Okay. Let me just try something a little bit. Try to analyze it a little bit, and then I'll modify it as I go down. Okay. So. Okay. Okay. So it always takes a little while to get these things sorted out so that they appear right on camera, so you don't have to do a second take. Right, good morning and welcome to Terence Payne Engineering. Okay, now again, student exercise. All this is for your own exercise. Now again, you need to write this out so you understand it, so that your brain knows what it's been asked to do. Okay, now reactance and impedance. Capacitors and inductors have a property called reactance, denoted with an X. On their own, they may be used with a form of Ohm's law such that V over I equals X. V will be the voltage, I will be the current. Both V and I are RMS values. The value of X depends on the frequency of the AC. And for the UK, AC is 50 Hertz, 50 cycles per second. Okay? And this is why they are called reactive. It should be noted that a pure capacitor and inductor does not lose any energy. A resistor, on the other hand, produces resistance by dissipating energy, but the value of R does not change with frequency. So a resistor is a passive component within a circuit. When a circuit consists of resistance, I'm just trying to put my teeth in. When a circuit consists of resistance, capacitance and inductance, the overall impedance is denoted with a Z. The units of R, X, and Z are ohms. Okay. Now capacitive reactance XC. When an alternating voltage is applied to a capacitor, the capacitor charges and discharges with each cycle. This means it goes fully charged, then it discharges, fully charged, and then discharges, because of the alternating frequency of the AC supply. Okay, so when an alternating voltage is applied to a capacitor, the capacitor charges and discharges with each cycle. This means that alternating current flows in the circuit but not across the dielectric. If the frequency of the voltage is increased, the capacitor must charge and discharge more quickly, so the current must increase with the frequency. The RMS current is directly proportional to the RMS voltage, V, the capacitance C, and the frequency F. Now again, draw these little diagrams out, and that this is just to give you an illustration only. Okay? Let me see if I can modify this on my camera in any way. Okay, I think I can. We should be okay there, I think. Okay, let me just go up a little bit. Now it follows that IRMS equals constant times VRMS times FXC. VRMS over IRMS equals I over constant times FC. The constant is 2 pi. So you can read this for yourself. I don't need to go through that. You can see the formulation there for yourself. Note that when f equals 0, xc is infinite. And when f is very large, xc tends to 0. This means that a pure capacitor presents a total barrier to DC, but the impedance to AC gets less and less as the frequency goes up. This makes it an ideal component for separating DC from AC. If we put in a combined AC plus DC signal as shown, we get out pure AC, but with a reduced amplitude depending on the reactance, the value of the reactance. Okay? And this is what we're talking about, DC AC input, okay, going through a capacitor. Now remember, you need a positive and a negative for your current to flow in the circuit. You can see here, the amplitude here is higher than here. We have a reduced amplitude. Okay. Now, work example number 1. Now, 15 volt RMS applied across a capacitor of 4.7 microfarads. Calculate the RMS current when the frequency is 20 Hz, 200 Hz, and 2000 Hz, or 2 kilohertz if you prefer. Now, let me just drop this down to show you what I've done. Bear with me for a second. I've dropped it down so we are, hopefully I can still see. Okay, now you can see what I've done here. Each one here gives you the process, but for me I just wanted to know how we got this, and you can see here that it's 1 over 5.90696 times 10 to the minus 4 equals 1,600 sorry, equals 1,693 ohms. It's alright, my mouth was just running away with my false teeth. Okay, so you can see that this value here is correct. Now, for me, I work in a different way to you. You have to find your own method of learning and your own method of application and process of calculations. When this value here comes by resolving these values here, okay? But for me, I just do this baseline first. Well, I do this baseline first. Then that gives this calculation here gives me this. That's just how I work, okay? You have to find your own way of working and your own method of style of learning and application. Now again, as I said before, put pen to paper, okay? Now you can see what's happening with the resistance. You can see what's happening with the resistance in each case. It gets less and less. As you increase the frequency, the resistance becomes less and less, and you get an increase in current flow. Well, it looks like an increase in current flow to me, but I could be wrong, okay? You make up your own mind on that basis, okay? Now again, this is brilliant work by a guy called DJ Dunn, okay? And I've used quite a few of his materials. I find quite useful. Now inductive reactance XL, okay? Now the back EMF produced by a varying current is E equals minus Lx rate of change of current. In order to overcome the back EMF, a forward voltage equal and opposite is required. Hence, in order to produce alternating current, an alternating voltage is needed. It can be shown that the RMS voltage needed to produce an RMS current is directly proportional to the current, the inductance, and the frequency, so that V RMS equals I RMS 2 pi FL. Okay? So see if I can just make him a little bit larger for myself and for you as well, hopefully, so that I can get it more fully on screen. Let me just make sure I'm not taking it off the screen. Bear with me for a second. Okay. Okay. Hence, VRMS over IRMS equals XL equals 2 pi FL in ohms. Now note that the reactance is 0 when F equals 0 and approaches infinity when F is very large. This means that a pure inductor has no impedance to DC, but the impedance to AC increases directly proportional to frequency. This is the opposite effect to that of a capacitor, and an inductor may be used to reduce the AC component of a combined AC and DC signal as illustrated. Okay. And here we have, this is what we're saying. We have our AC plus DC input signal, okay? You can see its amplitude, but here we almost have a smoothing out of the amplitude here. So we can dictate or manipulate the input and output signal as we wish, okay? This is what you can apply as a filter, if I remember correctly, but don't hold me to it. I'm just talking from past. Okay. Now here we have example 2. 15 volt RMS applied across an inductance of 4 microhenries. Now notice, sorry, let me just see if I can get my pen. 1 second, let me get my pen. Yes, I think you can. Okay, so you can see here that we have 4 microhenries, okay? And again, that's 10 to the minus 6, okay, henries. Very small, okay? And calculate the RMS current when the frequency is 200 hertz. (200 kilohertz). Now bear in mind that this is 200,000 hertz, okay? And you have here 200 megahertz, 200 million hertz, okay? That is 200 million cycles per second, okay? Let me see if I can get back. I'm losing. It seemed like I was losing a bit of light. Okay, now you can see here and 0.5027 milliamps, sorry, milliohms. Well, I wouldn't say that was million. 0.5027 megohms. Okay, I might be looking at this incorrectly, but bear with me. Sometimes these doesn't always give me the impression that I would like to express. But anyway, look at it for yourself and check it out for yourself. Make sure that you've got the right units. Okay? And here we got 29.84 kiloamps. That's a lot of amperage. That's 29,000 amps roughly. But as we increase the frequency, we get a reduction in the amperage of 2.984. And as we increase the frequency even further to 200 megahertz, the current goes down to 2.98. But you can see between the 200 kilohertz and the 200 megahertz, the amperage is the change is very small. Okay, it's only about 0.004. Okay, but again, write these out for yourselves. Make sure you have a knowledge and an understanding of them. Write them up. Put pen to paper. Okay, for yourself. Okay, get familiar with your working. Okay, don't just look at them on screen. Okay, look at the difference in the values here. Okay, look at the massive difference here in the current itself. Tremendous. Okay. Now do some of this work for yourselves. I cannot remember if I gave you the answers, but I will know in a moment if I did or didn't. But did I? Okay. Let me just go back up a little bit. Yes, I did. Yes, I have. Now you can see here, I've given you the answers for your own working out process. So let me just leave them there for a second so you can see them for yourself in full. Okay, let me just move in. Okay. Excuse me. Now let me just come back, pull you back a little bit there, make sure that you're on where you should be. Chemistry, okay. Okay, I'm hoping that you have been able to use this. Let me just drop this down a little bit so we can drop this into play. Okay, see what I'm doing. Okay. Okay, thank you. I hope you found this useful. Have a good day. And okay, thank you for your time. Have a good day. Bye bye.